Tony Hoare is one of the great pioneers of computer science. He made seminal contributions, including the quick sort, quick select, null reference, monitors with Prebrinch-Hansen, and what we now call Hoare logic. He received the Turing Award in 1980 and many other major awards afterwards. Image credit, Wikipedia. In this video, we are going to look at Chapter 1 of his book, Communicating Sequential Processes. It is a remarkable book, first published in 1985, with an effusive foreword by Edgar Dijkstra. The book presents its ideas in a carefully ordered sequence. It starts from basic operators and then progresses towards more elaborate applications. In this video, we will look at the first chapter through the lens of the Agda programming language. Chapter 1 introduces the basic concept of a process as a mathematical abstraction of the interactions between a system and its environment. It shows how the familiar technique of recursion can be used to describe processes that last a very long time or even forever. The second part of the chapter explains how the behavior of a process can be recorded as a trace, a sequence of the actions in which it engages. Many useful operations on traces are defined. A process can be specified in advance of its implementation by describing the properties of its traces. We will use Agda to specify and define processes and then prove laws about those processes. We will also revisit a problem we solved earlier in CTL and see how it works in this setting. Tony Hoare begins with the idea of an alphabet. The alphabet is the set of event names that are relevant for describing a particular object. In Agda, this idea becomes an inductive data type. The first example is a very simple vending machine with two events, coin and chocolate. Its alphabet is captured by the following type. Here we see another small Agda definition. This one shows the alphabet for a simple clock. The alphabet for clock has a single entry. It contains just one event, tick. Here we see the Agda definition of the actions for the die-hard problem. These are the events that the process can perform. This is the same definition we saw in the last episode. These events form the alphabet for a process that represents the die-hard problem. Here is an attempt to define a process in Agda. This definition follows the examples from the book. It shows how to model the broken vending machine. But there is a problem. With this definition, we can model only finite processes. We cannot model processes that run forever. The reason is simple. We define process Agda as an inductive type. The examples on screen show two finite processes. One accepts a single coin and then stops. The other alternates between coin and chocolate and then stops. To model processes that can run forever, we need a different idea. Instead of an inductive type, we need a co-inductive one. A co-inductive process does not have to end. It can always offer another step. Here we see the co-inductive definition of a process in Agda. This version can describe infinite behavior. A process is defined as a record. It is marked as co-inductive. X's. It contains one field called step. The step function takes an event from the alphabet. It returns either nothing or another process. This allows the process to continue indefinitely. Here we see the definition of stop. This is the version introduced by Tony Hoare on page 3 of the book. In Agda, it is defined as a co-inductive process whose step function always returns nothing. This means the process has no outgoing transitions. It simply stops. On screen, we now see two simple processes from page 6 of the book. The first one is the clock process. It has a single event tick. Every time it receives a tick, it continues as itself. This models a clock that keeps ticking forever. The second example is the simple vending machine. It reacts to two events, coin and chocolate. If it receives a chocolate event at the start, it cannot proceed. If it receives a coin, it moves to a new state. In that state, it accepts chocolate and returns to the original state. This models a vending machine, which serves as many chocolates as required. These examples show how co-inductive processes can describe systems that continue indefinitely. They also prepare us for defining more structured operators, such as prefix. Let us move on to prefix. Here we set up some infrastructure for defining prefix. To define prefix, we must constrain our alphabet. It needs to support decidable equality. To stay close to Tony Hoare's notation, we follow the type class pattern in Agda. We define a type class called has-dec-eq. It provides a decidable equality operation for any alphabet. On screen, we see instances of this type class. One instance is for the vending machine alphabet. Another instance is for the clock alphabet. Each instance defines how equality is decided for the events in that alphabet. With this type class in place, we can introduce the prefix function. In CSP, if X is an event and P is a process, then P describes an object that first performs the event, X, and then behaves exactly as the process P. We can achieve the same behavior in Agda. The code on screen defines the prefix operator. It checks whether the incoming event matches the expected one. If it does not match, the process cannot proceed. If it matches, the process continues as P. We allow the caller to pass the instances of our type class has-dec-eq as special kind of implicit arguments called instance arguments. We now see two examples built using the prefix operator. The first one is the broken vending machine. It performs a single coin event and then stops. This matches the example X1 described in the book on page 3. The second example is our first attempt at the Die Hard problem. It follows a fixed sequence of actions. Each action is introduced by the prefix operator. After the final action, the process reaches stop. These definitions show how prefix lets us build simple, finite processes in Agda. Here we see the definition of choice, introduced on page 7 of the book. Tony Hoare uses choice to model processes whose behavior depends on interaction with the environment. The environment decides which event occurs. The process then follows the branch associated with that event. In Agda, we capture this idea with the choice function. It takes two events and two processes. If the incoming event matches the first one, the process continues as the first. If it matches the second one, it continues as the second. If it matches neither, the process cannot proceed. The code on screen shows this definition. It uses decidable equality to compare the incoming event with the two choices. The result is a process that branches based on the event offered by the environment. We now move to one of the most important concepts in CSP, traces. This idea is introduced in section 1.5 on page 19. Tony Hoare defines the trace of a process as a finite sequence of symbols. A trace records the events in which the process has engaged up to some moment in time. In Agda, a trace is simply a list. To connect the process with its traces, we define an inductive relation called has-trace. The first constructor says that any process has the empty trace. The second constructor captures a single step. If process P accepts event A and returns P', and if P' has trace Sings, then P has trace A, followed by S. The code on screen shows this definition. It expresses exactly the same idea as in the book, but in a precise, type-directed form. On screen, we now look at a few examples of traces. The first equation shows a trace of length 2 for the clock. Both events are tick. This matches the behavior of the clock process, which always continues as itself. The second equation shows that stop has an empty trace. This is the only trace available for a process that cannot perform any events. The next two equations show the traces of the broken vending machine. It has two possible traces. One is the empty trace. The other is a single element trace containing coin. These examples illustrate how the hash-trace relation captures the possible behaviors of a process, step by step. We now look at a couple of laws on traces. The first law corresponds to example X1 on page 28. Tony Hoare states that the only trace of the process stop is the empty trace. We can prove the same fact in Agda. The equation on screen shows that if stop has a trace S, then S must be the empty list. The second lemma here is Law L7 from page 30. It says that if a concatenation of S and T is a trace of a process up to some moment, then S must already have been a trace up to an earlier moment. In other words, traces are prefix closed. The Agda code on screen proves this property. If the full trace S++ T is valid, then the prefix S is also valid. The proof follows the structure of the trace, peeling off one step at a time. These laws help us reason about the behavior of processes. By understanding how their traces grow over time, we now return to the die-hard problem. In this problem, the state is represented by a pair of jugs. Each action changes the state in a specific way. As we saw in the last episode, the state is captured by the jug's record. The function step J takes the current state and an action. It returns the next state. The code on screen is the same function we used earlier, with names adjusted to avoid conflicts. The behavior is exactly as before. Fill small and fill big. Fill the respective jugs. Empty small and empty big. Clear the jugs. The pour actions transfer water from one jug to the other. If the combined amount fits, the receiving jug is filled and the other becomes empty. If it does not fit, the receiving jug becomes full and the remainder stays in the other jug. We see one way to approach the die-hard problem. This version does not yet give us a fully satisfying process model, but it helps us connect traces with the underlying state machine. We start by defining a function from traces to states. In our case, we simply fold the step J function over the trace, beginning with both jugs empty. This computes the final state reached after performing the events in the trace. We can also show that a proposed solution is a valid trace for the process. The second equation on screen proves that the candidate sequence of actions is indeed a trace of die-hard OO. Each step is justified by a trace step, and the final result ends with trace empty. This gives us a concrete way to validate a sequence of actions against the process we defined earlier. Here is an alternative solution. We begin by extending the alphabet. We add a new event called success. You can think of this as the moment when Bruce Willis places the big jug on the bomb to defuse it. With this new event, we define a die-hard process that is parameterized by state. The process starts with both jugs empty. For any event other than success, it behaves normally. It applies the step J function and continues from the updated state. If the event is success, the process checks the amount of water in the big jug. If the big jug contains exactly 4 gallons, the process stops. If it contains any other amount, the process cannot proceed. This gives us a precise model of the puzzle. It also allows us to state the die-hard lemma shown on screen. The lemma says that the familiar sequence of actions, followed by success, is a valid trace of the die-hard process. I encourage you to try proving this lemma interactively. As you step through the proof, you can watch the state evolve and see the jugs move toward the required 4 gallons. That concludes this episode. Links to a few resources are in the description. The first is Tony Hoare's book, Communicating Sequential Processes. It remains one of the clearest and most influential texts on concurrency. The second is an interview in which Hoare explains the origins of CSP, including how the ideas grew out of a failed operating system project. It is a wonderful window into his thinking. You will also find a link to his Turing Award lecture, where he reflects on the principles that shaped his work. Finally, I have included a link to the full Agda code for this episode, so you can experiment with the definitions and proofs yourself. Thank you for watching.